Hello, everyone, and thank you for attending today's webinar, APEX EBSD, Making EBSD Data Collection How You Want It. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all the questions. A copy of today's slide deck is available in the resource list widget, which looks like a green folder. You can expand your slide area by clicking on the maximize icon at the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately one day after the webcast and can be accessed using the same audience link that was sent to you earlier or via the EDAX website. Now I'd like to introduce today's presenter. Matt Nall is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. Matt joined TechSem Labs, TSL, upon graduating from the University of Utah in 1995 with a degree in material science and engineering. At TSL, he was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, he joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has been involved in a number of roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that EBSD plays in materials characterization. In his spare time, Matt enjoys playing golf and pondering if changing the texture of his clubs will affect his final score. Now over to Matt.
Well, thanks, Jonathan, for that nice introduction, and thank you, everyone, for joining me. I'll say this morning because it's morning my time, but whatever time it is where you're watching. I'm very excited to be able to present this morning. This is part of our product introduction for our new APEX EBSD product, which is our new data collection product for our EBSD product line. So to give a little background on this, there's a few things we wanted to accomplish with APEX. First, we wanted to introduce EBSD into the APEX software platform. I'll detail in the next slide, but APEX was first released for the EDS product line and has been continually growing in capability and feature sets there. Bringing EBSD into this is the next step in expanding the characterization capability of this software platform. As part of this, we're aligning the EBSD workflow and operation with the EDS workflow. Our goal there is really to help make learning EBSD easier if you already know how to use EDS. We want to try to reduce the barrier of entry to becoming proficient at EBSD analysis. And then one of the key goals is to incorporate the best features from previous software packages. We've had two legacy data collection programs, one which is OIM data collection, the other which is Team. Both of these have had a number of features which users have liked, and we've tried to make sure we've ported those over into the APEX platform. But of course, at the same time, we've evaluated both and tried to improve on areas from both software packages to kind of provide the best of all worlds and provide the best available EDS and EBSD characterization package for our users. So just to give a brief background on APEX and APEX EDS, this was a software platform that was designed for 64-bit software or 64-bit architecture to take advantage of the 64-bit processors and operating systems. This allows us to handle larger data sets better, allows us to use Windows 10 more easily. And as we've done that, we've tried to build a very intuitive and user-friendly interface. We've really tried to emphasize having high-quality, accurate data, giving good feedback during that, and to make analysis easy. With APEX, it started as an entry-level system, and the feature set has grown on the EDS side into a complete microanalysis package. And then, like I mentioned, by adding EBSD, we're taking the next step in adding structural characterization to complement the chemical characterization capability. And of course, in my role as product manager and as we develop the program, we're always thinking about our users and thinking about the different types of users. So I've put here kind of a very basic subset, but we think we provide products to lab managers, to scientists and researchers, to students, to SEM operators, and also from our perspective to SEM vendors, the folks who sell the microscopes. And as we work with each of these type of users, they all have specific needs and things they need to do. So we've really tried to design APEX to address these range of requirements to each different user type. So some of the things I'll talk about are addressed for one specific subset, others to different user bases, but we've tried to make sure we've addressed a range of user needs in designing the product. So the first thing I want to introduce is the user interface. It's of course the first thing you see when you use the application. And so really we've tried to design it to be easy to use, and we've built it off of a ribbon bar type of an approach. This is similar to what you'd see in Microsoft Office type applications or MATLAB. It's a pretty common user interface paradigm. We've designed it so that the icons we use have both graphics and text to describe functionality. So the text makes it easy to understand what the icon refers to, but having a graphical icon makes it a little bit easier to remember on repeated use. The functions are organized into task-specific pages, so it sort of self-organizes your work. It's all in front of you. One of the terms is kind of what you see is what you get, and it's sort of applied to this, but you're able to see the available functions a lot easier. There's not as many tiered hidden menus. And so you're able to see the different things you can try to do with the program. This increases the discoverability of these features. And in the end, it enables quicker learning of the application. You're able to see what you're able to do with it and get through it. There's a workflow approach, kind of working through the tabs and then working through the workflow on the ribbon bar, sort of left to right. So these are just a couple of different images of the EDS and the EBSD application ribbon bars. Again, very similar type of approaches. We've tried to keep them generally consistent, so tasks that are similar in one follow the same type of flow on the other application. This is just an example of the ribbon bar for the pattern page. So in this case, you can see in the top, we see the different tabs. So there's one for camera control, there's one for working with the pattern, there's one for collecting scans, there's a phase page, a HUFF page, and a calibration page. In it, in this case, this is the pattern tab, so the focus right now is sort of on the SEM image and on the pattern we get with a little area where we look at the solutions. And so we're able to focus just on that pattern image. But one of the key fundamental features of the program is that this is all configurable. So each page has a variety of different view windows that are available. So in the previous example, we could see we had a pattern window view and we had an SEM image view. Each page has a number of preset layouts that bring up certain view windows. So in this example here, you can see there's what we'd call a basic view. We have a solutions-focused view, an EDS-specific view, and then you can also see we can save custom layouts. So for all these different window views, we can move them around, we can resize them, we can float them, we can dock them. There's automatic alignment tools available, and they can also be overlaid and tabbed. So if you wanted to see 3 different things in sequential order, you can set those up as tabs. And these views are also compatible with multiple monitors. So if there's something you always want to see, you can just slide it over to a second monitor, and that'll always be up during the analysis. So this harkens back to the original title. Basically, you can configure your workspace how you want to see it, how you want to operate. And I think that's key going back to the different user types is that as we've taught people I'm doing this a long time now, if I don't want to even add up how many years, but we know different users are focusing on different things. A lot of times this is being used as a research tool, so it's doing new and novel things often. And so, you might want to approach the software differently for different types of applications or different day-to-day use. And so you're able to configure and save this layout basically how you want it. It can be tailored to your specific needs. So this is just some examples. This is the basic layout for that pattern page, just the general basic information. If we want to go to the solutions page, we get a little bit more information. We start getting a camera control view. We get a pole figure view. If I want to bring in the EDS information, it now brings in full spectrum collection. It brings in the quant results as a table there. And then if I want to take any of these and now make them how I want it, I add some different windows. I move them around, and then I save this as a custom view. So again, it's sort of a great tool to be able to say I can rearrange position, size, and add and subtract to get just what I want to see when I'm working on a specific problem. The other thing that's surprisingly more nice than you would expect, I've grown to like this more and more, is that you can use different color schemes for the user interface. And so one, you can just get it to what's your preference. I think we're all more and more familiar with smartphones now where you can customize your phone to get what you want. Software is sort of following that same trend. So we also are able to complement the user interface that would be available on your microscope. It makes it look like a nice complementing tool. There's a dark mode that can reduce eye strain. It also works well for different, when I've done remote presentations, people have chosen that when I've asked them to choose which one they want to use. And it's selectable as a user preference. So each user can have their own color scheme selected. And so this is just an example. This is a dark mode, a gray mode, and a light mode that are all just selected. So it's not changing the content, just changes the colors. Okay, so those are some of the introduction to sort of the look and feel of the software. But of course, that's not the primary goal of the software. The primary job of our data collection process is to be able to capture and index an EBSD pattern. And when I say the term indexing, what I mean is what I'm showing here is we're trying to determine the crystallographic orientation. So we capture the pattern. The term indexing means we're finding out where the planes are located, which tells us the crystal orientation. And that's really what we're trying to do. So like I mentioned, we have a range of users, and when I looked at the attendees list, there's a range of people. So I apologize that this is a review for some of you, but it's good introduction to the fundamental engine that's driving APEX EBSD. So to be able to index a pattern, there's really three things we need to be able to do. We need to know what we're trying to match it against. We have to define our reference crystal structure. We'll do our band detection, and then we'll do our orientation determination. So we'll first talk about defining this reference crystal structure. So just as a little overview, when we think about what happens when the electron beam hits a crystal, the electrons penetrate into the sample. Of course, it has to be polished well enough that this now goes in and scatters and diffracts. And the electron beam diffracts off of certain crystallographic planes. So the schematic here on the left shows a given crystallographic plane. We get coherent diffraction from that. The diffraction from that plane projects out, and it's intercepted with our EBSD detector. So in this case, we're looking at the phosphor screen. So we're looking at the projection of this plane onto the phosphor screen. And the projection are two oblique cones. And so when those cones hit the phosphor screen, it ends up looking like a band. And so we have a center line trace of that band, and then we have two band edges that have a slight curvature to it. But when we look at it, they generally tend to look like straight lines. And so this schematic shows the diffraction occurring from a single plane. But of course, there are multiple planes diffracting in the material. And so the pattern that we see is the overlay of the projection of multiple planes diffracting along with a scattering intensity background. So I don't actually talk much about it in this part of the talk, but of course, remember we are doing a background correction to enhance the diffraction signal to allow band detection. So when we look at this, what we want to do is we want to be able to find the position of these bands and measure the angles between them. Once we know that, we know where the angles are located geometrically, which tells us the crystallographic orientation. Just as a quick reference, when I mentioned crystallographic planes, these are just basically slices within a crystallographic unit cell. The important thing for us is that the planes with a lower index value, so the HKL value or lower numbers, generally tend to have a higher atomic density, and so these tend to diffract more strongly. So one of the tricks for preparing for EBSD is we have to tell the software which planes we think are going to diffract, and generally they're these more lower index planes that have stronger diffraction. And so to be able to do that, we have a couple of tools in APEX. First, we have our structure file generator. And so this is a tool that allows us to create what we call a structure file or a material file that contains the crystallographic structure, the crystallographic symmetry. It contains the lattice parameters, and it contains the strongest list of diffracting planes, which we call reflectors. So with this tool, we can predict those planes using kinematical diffraction theory. So what we have to do to do this is we input in the atomic positions within the unit cell, which are kind of shown in that little cartoon here for, this is a face-centered cubic structure, aluminum. We put in the lattice parameters, and then it looks at the structure factor intensity calculations based on crystallographic symmetry and the scattering factor for that particular atom to come up with a list of reflectors that fill that space. That's what we see in the bottom left of that screenshot, and then we see a simulated pattern from that. And so if we know this information, which we can get from, you can get it from the web, you can get it from the Open Crystallographic Database, you can get it from different books and articles and papers, you're able to input these in and predict a crystallographic structure. Now, of course, we also provide a library of materials for the most common materials. So we have a library of around 500 materials, which covers your most common metals, minerals, semiconductors, ceramics. But if you are starting to look at more novel materials, you do have this tool available to calculate these structure files. Once we have this list of reflectors, the software then has to build what we call an interplanar angle lookup table. So just so you're aware, what it does is we identify these planes, or HKLs, that have the highest intensity. So for an FCC material like aluminum, it's the 200, the 111, the 220, and 311. Those are the ones we generally expect. The software uses the crystallographic information to then determine all the equivalent HKLs or equivalent planes. We then form all the possible pairs between these planes, and then it calculates the angle between all these planar pairs. And then we just put that into a table, and we throw out duplicates, and we sort by angle. So we have this lookup table now. So if we look at that first entry under number 5, the angle between the 200 and the 311 is 25.2 degrees. So as we measure angles in the pattern, we can compare them to this lookup and start to figure out which line correspond to which crystallographic planes in the material. Okay, these phases, in addition to being calculated, we have what we call a phase management tool. So all the different libraries and databases we have can be accessed and searched through APEX. We can search by name, we can search by element, we can search and filter by crystal structure. And then in addition to the database that's supplied with EDAX, we can access other third-party databases, including the ICDD PDF4 database, the ICSD Inorganic Crystal Structure Database, and the AMCS American Mineralogist Crystal Structure Database. So those extend the capability into basically all the the crystal structures that are used for, say, X-ray diffraction pattern matching. And so that leads us to the next step in the pattern indexing routine. Once we know this reference crystal structure, we have the interplanar angle lookup table. Now we have to find the bands in the pattern. And we do that with what's called the HUFF transform. So that's basically the problem we're looking at, is we're looking at this pattern on the left. We see these bands or these lines. We transform it with this HUFF transform, and I'll explain what that is, but the image in the middle there is the HUFF transform space of the pattern. The image on the right is showing the bands that are found with that HUFF transform. So that's what we're trying to do at this stage of the application. So just to give some quick background for the HUFF, basically it's a transform similar to a Fourier transform. So it's just mathematically changing the XY space of our image into the rho theta space of the HUFF value for the intensities. And the important thing is, if we look at this schematic on the bottom left, if we pick a point in XY space, you can imagine there's an infinite number of lines that pass through that point. It's like a second hand moving around an analog clock, is that, you know, everywhere on there's a line that goes through that, and each line can be defined by a rho theta value, where the theta value is the angle to the line normal, and the rho value is the length of the vector to that line. And so for any given point in XY space, there's a curve that corresponds to all the possible lines passing through it. And then if we go to an image where we now take a line in HUFF space and we put a number of points along that line, each point, of course, has a curve associated with it. But if those points are associated along a line, all those curves converge at a single region of HUFF space. Okay, so we can show that schematically here. If we look at it in black and white space here, this just shows a line with a number of white dots there. We see the curves in the HUFF transform on the right, and we see, as we sum up the intensity along those curves, we get a bright region where they all converge. We take this model to now, instead of dots along a line, to a single line. You can see now we get a very characteristic shape in HUFF space for a line. So there's this bright area with the edges sort of falling off. And so that's, of course, an idealized case, but if we throw a pattern in, we get the same thing. So the lines, all the lines in the pattern have a higher intensity. So as we transform those into HUFF space, those form characteristic peaks in the HUFF transform. You can see on the image on the left, they sort of have a very characteristic dark, light, dark fingerprint. And so the software has a HUFF transform that's designed to find those bands in the HUFF space, the points in the HUFF space, which corresponds to bands in the EBSD pattern. So that's what we're trying to do. Of course, it's the key to being able to index a pattern. If you don't find bands correctly, you know, it doesn't matter what your indexing engine compares it to. It's garbage in, garbage out. So there's a lot of work that goes into finding the bands correctly in the HUFF page. So we have a dedicated page for this with a very dynamic feedback as you change settings here. You see what happens both in the HUFF space, but also in the real XY space. So in this screenshot, the bands that are shown in that pattern, the colored overlays correspond to the bands that are found in the HUFF. So you're able to see, are those bands actually real bands that I can visibly see? And so you can adjust. You'll adjust these because sometimes we have to change the acceleration voltage. Sometimes if you're looking at different materials, you'll have varying bandwidths due to lattice parameter effects. Sometimes you have to adjust this because of the complexity of the pattern, how many lines you're looking for, and also the camera resolution you're operating at. And so that's important because the camera, when we do our camera optimization routine, which I'll talk about, it can also automatically adjust the HUFF based on that camera optimization selection. And then, of course, you know, we also know that this can be a little overwhelming at times. So there are easy default settings for basic operation as well. For your most common materials, the defaults often work pretty well, but it's expandable as you go beyond that. Now, of course, as much as I love our HUFF page, it's always important to note that even as we tweak the HUFF, and you can tweak it to get it perfect on one pattern, then when you collect the next one, it's not perfect. We know we're collecting, hundreds of thousands of patterns. The HUFF band detection is not always 100% correct. And that can be for a variety of reasons, including, the grain size of material, how deformed it is, the sample deformation state, how complex the crystal structure is. If you're looking at multi-phase samples where different phases might need different HUFF settings, the level of sample preparation condition, all these can influence band detection. So we never think it's going to be 100% perfect. So what that means is the indexing approach we use needs to have some tolerance for imperfect band detection. And so this cartoon here basically shows a schematic of if we're near a grain boundary, the interaction volume of the beam may sample a little bit from this top red grain and a little bit from this bottom blue grain. So the corresponding pattern at the boundaries have a little bit of an overlapping pattern that we want to try to deconvolute with our indexing approach. So that leads us to how we determine the orientation, and we want to make this fault tolerant for band detection. And so the way we do this is with what we call triplet indexing. And so the reason we do this, like I mentioned, if we find all the bands correctly, indexing is generally easy. This is a little bit of a simplification when we start talking about things like pseudosymmetry, but if we find the bands perfectly, indexing is generally easy, but we know it's not always perfect. And so we want to be able to handle that, but in addition to wanting those things, we also want it to be accurate and we want it to be fast. And so the approach we have, we want to be able to support our Velocity Super Camera, which indexes live at speeds of greater than 4,500 index points per second for materials, for some materials. So our solution for that is our triplet indexing engine. Now this is not a new thing. This is something we've been doing for a long time. It's proven, it's time tested. We know it provides higher indexing success rates even on difficult materials. But of course, when we're looking at indexing engines, we're always evaluating compared to other alternatives. We're still very happy with triplet indexing. And in addition to that, I'll describe how it provides a confidence index solution or a confidence index value for each solution. So for triplet indexing, what that means is we're taking sets of 3 bands, so sets of 3 or triplets. And the reason is, if you imagine we look at 2 different planes, we can measure the angle between them and find a match. But what we don't know on this basic level is if I find 2 bands and it matches an angle, is the band on the left the 111 and the band or is the band on the right the 111? We can't tell them apart. We only know the angle is there. So by finding 3 bands and working on 3 band sets, we can uniquely define which band corresponds to which plane very easily without having to bring other solutions and other measurements into the issue. And so we'll show this on this third triplet one here. So this shows 3 different bands here. So we measure the angles between them. And by looking at the matches, we can see that one angle would give us a 111-200 pair. The blue line intersection there would be a 111-311 pair. And then the third one would be a 200-131 pair there. And so by pairing all 3 of those together, we then know, well, which band's the 111, which one's the 311, which one's the 200. So a single triplet index can tell us the position of those bands, which band is where, and of course, once we know where the planes are spatially oriented, we can then represent that orientation either as a set of Euler angles or as an orientation matrix or in HKL UVW type notation. Basically, we know the crystal orientation once we know the band positions, and that's all done by letting us know what the sample tilt is, what the detector geometry is, and where these planes are. Then there's some matrix math that occurs to determine that orientation. So this approach works for regular EBSD. It works for transmission EBSD. We just need to define the reference frame of the sample when we make these measurements. And typically that's done through reading the stage tilt value, and inputting any pre-tilt holder that's used as well. Now, when we do this, of course, we don't expect our band detection to be perfect in terms of the line positioning either. We have some tolerance to how well we find the band. And so in this particular slide, we put down 5 degrees, so it kind of shows a window of opportunity. Generally, we run at 3 degrees as a default tolerance. But I emphasize this because what it means is that for a given triplet, we may find more than one possible match based on this tolerance. And so that allows us to sample more what we call votes. And so to give an example of that, what we see is that when we look for lines, of course, to find an orientation orientation solution, we need just 3 lines. That will give us one triplet combination. But what we want to do is we want to look at more than 3 lines to get multiple combinations that allow us to ignore possibly rogue bands that aren't detected correctly. So generally, we look between 7 and 10 bands. So 7 bands give us 35 different triplet combinations. 10 bands give us 120. And for each triplet combination, we can go through and do this indexing routine I've shown on the previous slide. So just to show this, this is an example where here's a pattern. We're looking for 5 different bands. For 5 bands, there are 10 different triplet combinations. So if of these 5, I can find a solution, I take a set of 3 lines from this. I find a solution that matches very well and it gives us a good fit index. I can take those same set of lines and find a second solution that matches the center one. So if we look at the center, you can see where that 211 is. I'm going to call it magenta horizontal line, the yellow and the red line sort of match that zone axis okay. The other lines are a little bit off and one's really not shown in the solution. So this provides a higher fit value. It doesn't match quite as well. And then there's a third one. So we can see for these particular set of 3 lines out of 10, there are 3 different solutions that are possible. And so if we go through all 10 possible combinations, which are shown here as different color combinations, all of the solutions or all of the combinations match a single orientation, which we call solution 1. So as we go through, each one of those receives what we call a vote. Now, the red, yellow, magenta also received a solution for a different orientation, which we've called V2. And then the yellow, blue, magenta also received a solution that's different than the other one. So solution 3 received a vote. So when we go through all the triplet combinations and we tally all these votes, the first solution is the one that has the most number, and in this case it's 10. And then the second solution has 1, the third solution has 1, and there might be more. But in the software, we can see this voting tabulation. The reason we like this is that, first of all, the top solution generally matches the actual solution. And that's what we see here, is that our first solution, the bands actually match the overlay very well. But the key is we don't really want to have to rely on visual inspection to assess if the indexing solution is correct. Again, we want to let this collect millions of points without us sitting there watching it saying yes or no to each one. So that leads us to what we call our confidence index. This is a value we have that provides a metric for how well we think the automated routine worked for a given pattern. And so the confidence index, or CI, is defined as shown here. It's the number of votes for that first solution in our indexing table minus the number of votes of the second solution divided by the ideal. And so the 2 concepts I want to show here, the numerator in this definition tells us how different the first and second solutions are. And why that's important is that we may have a solution that matches, if we think of 7 bands, 35 times, but if we have a second solution that matches 34 times, we know when we subtract that, the numerator is small, so our confidence index will be low. That tells us we're not particularly sure between one solution and the other. And that's important information. It does not necessarily make our job easy, but it does tell us to say, hey, there could be multiple orientations that are close to this. And that's where we have to start evaluating things like pseudosymmetry, or if we need to add more lines to the HUFF and tweak things to try to improve that numerator. the line on the bottom, the ideal, using that as a numerator versus that top difference allows us to say whatever our number of votes on the top, the unique solution is, how's that occurring relative to the number we should get? So ideally, if we expect 35 votes, we want to get close to 35 votes for the top solution. And so that helps scale to say, you know, yeah, we're getting a unique solution, but we're not getting as many votes as we should be getting. That would also lower our confidence index and have us look back and say, you know, do we need to adjust our material files at a different phase than we're expecting? So the confidence index can give us a lot of information to assess how well the indexing engine is performing. And this is a curve we've shown a long time that kind of shows, you know, it's a value that can go to 0 to 1, but it's not a linear scale. Basically, once we get a confidence index greater than 0.1, we start to feel pretty confident in the solution. And even though there's a confidence index of 0, there's still about a 40% chance it's still the correct solution. So we have some routines in the software to help deconvolute some of these things to say, hey, we want to identify what are the high confidence points coming out of our indexing engine. Those are the ones we really want to analyze, and we can do that also in OIM Analysis. And the reason we like this, going back to this example, is it helps when the band detection is not perfect. It helps us deconvolute these overlapping patterns. And I can show the example from this. So this is a map across a grain boundary. The image quality map there on the top left shows where the boundary is located. The map on the bottom left shows the confidence index map. So within the grains, our confidence index is very high. We can see it's red is close to 1 because we're doing that very well. But near the grain boundary, the confidence index drops. And the reason is the patterns overlap. We find bands from one grain and then bands from another grain. But if we look at the orientation map on the top right, the orientations we find across that boundary, it's a very sharp step function. We find the orientation difference very well, even though the confidence index goes down. And that's basically telling us the indexing engine is working as designed. And even though the band detection is not perfect, we're finding the right orientation. So that leads to the question of saying, well, if triplet indexing is good, why don't we look at more than triplets? And the trade-off here is to say, you know, for triplets, we show there in the sets of 3 the number of combinations. If we go to sets of 4 or sets of 5, the number of combination increases, but as we miss bands, the fraction of bands that correspond to the correct solution decrease. So by looking at triplets, we're getting this pattern deconvolution effect, but we're also getting higher efficiency. We can get faster processing times. We're not having to analyze solutions that aren't the correct ones. And so I can show this in this little graph here where it's indexing efficiency. It may be a little small in the text, but basically I'm showing what's the fraction of points or fraction of votes we're looking at that contribute to the right solution if we miss one band. So those are the curves that are the top 3. So basically we see that looking for at triplet combinations gives us the best results compared to 4 or 5 bands, and then missing 2 bands, triplets still above both as well. So the efficiency of our indexing and the throughput of our efficiency is better using triplets than using 4, 5, 6 band combinations. And again, this is important because we're integrating this with our Velocity Super detector that runs at speeds, you know, up to or greater than 4,500 index points per second. And at these speeds, we can get 99% indexing success rates. And by that, we're defining the points with a high confidence index from the sample. So we get performance, we get speed out of the indexing engine. Now, of course, if we have a nice fast camera like that, we have a fast indexing engine. We've have features now within APEX that take advantage of this. So one of the ones is batch mode operation. So with batch mode, we can collect sets of data that are predefined. So in this case, this is showing 3 different scans where we can change the magnification, we can change the scan area, we can change the step size for these different ones. We can do line scans, we can do freeform scans, we can do combo scans as a batch scan, and then these can all be run as a batch, as a set. that allows users to use their SEM more efficiently. You can set it up and let it run overnight, set it up and let it run and come back, later in the day, and multiple scans will be collected from multiple regions or multiple samples. The other application where this is very useful is a combo scan. And by combo scan, what we're doing is we're collecting data from a large area by taking a regular scan, then moving the stage to an adjacent area and collecting another one, and repeating this process and then stitching it back together. And so for this, there's a number of features we've put into APEX to sort of improve this process. First, there's an automatic stitching routine to put things in together into a single file. There's oversampling that's available if you want to optimize the fit between adjacent fields. And one thing I didn't put in here is you can also look at the full width, or you can look at a square field of view when you're doing these combo scans, so that your X and Y axes are the same. The reason that's important is as you start to deflect the beam out a little bit further, you can get more imaging artifacts just from the fact that we're imaging a tilted sample. So by going to a square field of view, it helps minimize some of these trapezoidal distortion effects and improves the restitching, the refitting of the data back together afterwards. So these are two features that are really nice with APEX. Again, APEX has a 64-bit architecture that allows us to work with and collect larger data sets than were previously available with TEAM or OIM data collection. And then this is another thing that's a pretty important feature for once we've collected the data, is we've tried to improve on the data management strategy. And so I've tried to simplify it into basic points, but first we can save data where they want. So you're not locked into necessarily a specific folder or something on a hard drive or any hard drive. So you can specify the drive you want to save your data and the folder location. You can name the data what you want. You can give it its own unique name. You can move the data easily. This is especially important for EBSD, where we know a lot of users will use OIM analysis away from the microscope to actually analyze the data. So the data can now be saved into a single HDF5 file. And so the HDF5 is a hierarchical data format file that allows us to basically create a project tree in the data file itself. And so as we have a single file, we can move it from one computer to the other just as a single file without having to worry, did I forget something, did I leave something behind? And so it's easily transportable, but it carries all the data with it. It can carry multiple patterns, it can carry multiple scans, it can carry EDS and EBSD data together. And so, and by having it organized in a project tree, it's sort of an intuitive data organization. You can see when we collect the data, it can give default names. So that top area where I collected data, OIM map 1, OIM map 2, pattern 1, 2, and 3. But I can also rename these: deformation zone, base metal, nickel pattern, titanium nitride pattern. Area 3 has a combo scan. So you can do it quick and easy if you want the computer to just give it default file names, or you can put in the specific information you need. And having this for data allows things like APEX review and OIM analysis to be able to take this data away from the microscope into a remote PC and then carry on your work to make your SEM time a little more efficient. And then your analysis can be done at your own pace and using the tools available for that. Of course, within APEX, we can also save all the patterns. It's just basically a checkbox to save them. We're seeing more of a driving force to do this. So saved patterns can be used for re-indexing and OIM analysis. It can be used for NPAR, for Prius, for dictionary indexing, for HR EBSD, and then for custom applications. So you're able to access these. You can export them out as different files if needed. APEX provides what we call smart camera optimization. Basically, sometimes you want to run the camera fast for throughput. Sometimes you might want to run it slower to get good EDS counts. Sometimes you might want the best possible patterns for a single phase ID type application. In this case, sometimes we want to look at it for atom probe assist samples. And so we have context-sensitive options that allow you to select how you want to run the camera. It uses the signal feedback from the microscope and the EDS detector to make sure those values make sense relative to your SEM conditions in your sample. And so this tool makes collection reliable and fast, especially if you're not used to using the camera. There can be a number of settings there, so it kind of guides you through what's going down. It gives you visual feedback to how the camera is being optimized. And you can access this both from the ribbon bar, but also from the camera detector panel as well. And of course, if you don't want to use this, manual setup is also available. A similar smart function is being able to select the step size. So for any given magnification, you can select a coarse, medium, or fine resolution. Based on the area you're looking at and that magnification, it will then select a step size rounded to a value to give you an approximate number of points. This helps for consistency. So if I look at 5 samples at 500x and always select the medium step size, that will be consistent for all 5 scans. And having that consistent step size makes analysis when you're looking at things like point-to-point misorientations and kernel average misorientations more consistent if your step size is consistent, because you're averaging deformation gradients over a spatial scale. So you want to have that consistent. And then of course there's the option for a manual step size selection and specification as well. I mentioned it's compatible with Prius, and so Prius is an option we have where we use the EBSD detector as a multi-channel imaging detector. And basically within APEX, there's what's called the Prius Live mode, which has 25 preset ROI regions. We take the phosphorus green and divide it into a 5x5 array of detectors. Each detector, we can create its own image. Prius is also used in APEX for the Prius collection mode, where we have the 3 predefined ROIs, where this is an example from a thermal barrier coating from a nickel superalloy, where the image on the left comes from the top ROI, where we see atomic number contrast. In the middle, we see orientation contrast, and in the bottom, we see topographical contrast. And then with the save patterns, it also supports Prius analysis mode. With the save patterns, we also support NPAR. This is an approach where we average neighboring patterns with the center pattern to improve signal-to-noise ratio of the patterns. That allows us to improve indexing rate. So this just shows schematically our traditional indexing maps there on the left. As the patterns get noisier, indexing performance goes down. We run this through NPAR, indexing performance goes up. I went one too many, sorry about that. APEX, we have a unique feature in that we use a hexagonal scanning grid. And so this is something that as we collect larger and larger data sets, it's harder to see. So I've zoomed up into one. There's a few advantages to this. First of all, it gives us a greater density of data points for a given step size within a given area. We get more points, which allows us to characterize boundary shapes and sizes a little bit more accurately than a square grid would give. It gives us constant distance between neighboring pixels. This is useful when we think about our misorientation analysis and we're looking at local misorientation between points. If we're taking the average between a neighbor, we get 6 nearest neighbors with the same distance. It's good for averaging. With a square grid, you get four neighbors of one distance, and you get 4 corners of a different distance, so you have to average those a little bit differently. And the hexagonal grid allows us to look at things like triple points. So triple points are important for how grain boundaries behave. With a hexagonal grid, we can find these triple points. We can reconstruct boundaries. And so it's something we've had for a long time that's sort of hidden under the seams, but I wanted to make mention of it here. I mentioned before, APEX is designed for 64-bit applications, allows us to handle larger data sets more easily. It's also compatible with the Windows 10 operating system. We see more and more users. Again, I mentioned user types at the beginning. We get users who say our IT group needs us to be on Windows 10. So this is a platform that's designed with Windows 10 in mind. We have multiple user modes. We know these are sometimes used in multi-user facilities. And so when we do this, we can have our own APEX-based login to control things, or we also have the option to use the Windows authentication. So if you have a specific domain login you use, we can piggyback off that to define the user. And then we can have user-specific settings. And some of those can be, the cosmetic things. I want my windows to look like this. I want them to be this color. But some of them are also limiting what functionality is available. With EBSD, we're inserting a detector after the sample is tilted. We're moving stages for combo and batch scan. If you're managing a facility, you might not want to give users permission to do that until they've been fully trained on keeping the detector safe. And so with these multi-user modes, you're able to manage that functionality for different users. And then thinking that we have users around the world, we also provide multiple language support. So if you want your buttons to have French or Chinese or German text, those are available as different languages. And then this is another feature we're really excited about. We'll also be having cloud-based updates. You can basically make sure you have the latest and greatest software. Of course, we also know that some of these systems are installed in places without internet access for security reasons. So in those cases, you can download these updates and then bring them over on a physical media for when the network's not available. But basically, this allows users to take advantage of the latest features and updates. That oftentimes we have questions coming in, and the first question we're always asking is, what version of software are you using to make sure that you have the full suite of features that have been developed. And then there are also some simulation tools for showing things like orientations, misorientations, planes, indexing. Sometimes these are being used by students. It's a great tool for learning the fundamentals of crystallography, of indexing, of how the pattern relates to the crystallography, how pole figures relate to the patterns in the crystals. It's just a nice suite of tools, and these are available both in APEX and in OIM Analysis. Of course, I haven't mentioned it too much, but this is fully integrated with the EDS side. And so it's very easy to collect simultaneous EDS, EBSD data, both in pattern mode. If you're collecting a single pattern, you can basically say, I want to collect my EDS spectrum here as well, and you'll see the spectrum alongside the EBSD pattern. You can do your quant information right there, use that to help load what the phases are, and then do your indexing. But you can also do it during your mapping. So you can specify, here are the elements I'm looking for. I'm going to collect those. I'm going to show those elements, and we have the full spectrum data set in the background. We have what we call our APEX suite mode, where you're able to switch between EDS and EBSD focus. So for EDS, if you're I want to really focus on spectra, I want to collect an EDS line scan, you can do that on the EDS focus. If I want to do EBSD, I can focus on there and switch between the two dynamically. And all this data is saved to a single portable HDF5 file. So it's a very seamless collection, seamless data storage for users. And just to give some background for APEX EDS, this version, we call this version 2.0, it builds upon this successful introduction of APEX. We've had a few versions, but 2.0 is sort of the next step. So some of the features include smart phase mapping. We have a revamped quant engine. We support the Octane Elite detector, which is our high-end detector. Multi-user support, expect spectra during compositional mapping. I mentioned the HDF5 file. We have advanced reporting. We have the APEX review tool for offline analysis. So not only is this an EBSD tool, it pairs with a fully functional EDS tool. And then we can think about also that we have on the EBSD side, we have OIM Analysis. And so when we evaluate an EBSD system, oftentimes the focus is on sorry, that jumped ahead. There we go. We focus on the detectors and the collection software. Oftentimes in practice, this is the first step, really, in understanding your materials. We have our OIM Analysis package that I'm not sure, that keeps jumping around. I'm sorry about that. That allows us to create maps, charts, and plots to really analyze your material. So why I mention it here is that APEX can then use OIM Analysis to piggyback on the functions that are available to do some really powerful analysis. And we do that through what we call our template. So within OIM Analysis, we have the ability to define templates where we take a certain analysis and we save it as what we call a template file. And generally, we've used these in the past to share templates and things, but we can now use this for what we call template-based reporting. And so what we're able to do is we take these templates which save all the different functions in OIM Analysis into a template, and we can use it to create a report. And so this is great for customers who have repetitive analysis, but it's customizable. You can really tune it to what you're doing. So it's something we can define an OIM Analysis, but use an APEX for it. And so I wanted to show a little bit of the workflow for this. So the first thing we do is you take your data into OIM Analysis, determine what you want to do. So in this case, I've just created a little map where I'm creating a cam map, a grain map, an IPF map, a Prius map, an image quality map. So if you're a lab manager, you might tell your customer to say, hey, you tell me what you want, or you set up what you want, and then you save this as a template. That's just as easy as going to export as a template. You save this as a file. And within this, you can have maps, charts, plots. You can adjust the colors, the ranges, the settings, anything you want. You can really get it tuned in. Once you have this template, you can then define a report by the template. So within the report designer, you say, I want these are the outputs that are available from the template. You can then position these within a Word document for here's the size I want, here's where I want the legend, this is how many pages I want, this is where I want to show the step size, or this is where I want to show the sample name. You put all that together to create a report layout. So then, when you run the report, it populates the report with the data you've requested. And then once you have this, you can run subsequent reports, just basically jumping to step 4. And so it's very great for repeatable analysis. You get a Word file report. It can be used from APEX, so you can just say at the end of my data collection, generate this report, or you can also still use it from OIM Analysis. You can take your data and say, now I want to create a report just there as well. It's used in both applications. And it can be used for a single set of scan, or you can do a batch and use batch reporting to look at all the scans in the reporting. So with that, I'm going to skip ahead here to this. To just kind of summarize, we're about at an hour, so I don't want to, I'm going to skip a couple of the slides I had, but I just want to summarize some key features for APEX EBSD. Again, it's an exciting new data collection project. We think it should bring a lot of what folks have asked for who have used both our legacy OMDC and our team products, and it brings them all together. Improved intuitive user interface using a ribbon bar, this customizable layout and color schemes. You can have it how you want it. It grows and adapts as you use it. This improved reporting using OIM Analysis templates. We think it's a way to help users understand OIM Analysis, make it more accessible. It has the batch scans. It has the combo scans. It has improved for both of those. 64-bit applications for larger scans with our faster cameras. And then this leading indexing legacy performance. It uses the Triplet Indexing, the Confidence Index, and the high speeds of the Velocity camera. So it really provides a really comprehensive data collection tool for our users. So with that, I'd like to sort of give a couple little shout outs to some upcoming things. This webinar is something we try to do monthly. So next month, it's a presentation by my colleague Rene Duclos, where he's showing our Clarity direct electron detector, showing some of the new things we can do using a direct electron detector compared to conventional detectors. So that's coming up on November 21st. And we like doing these webinars, and so we also wanted to just kind of let people know of some of the additional resources that are available. So we have these webinars. We have them archived available on our website. We have our blog where we publish a number of interesting little articles using our tools for a range of materials. We have a number of different movies on the website and on YouTube. We post things to LinkedIn and Twitter. And of course, if you have any questions, you can always reach out to our info.edax@amatech.com address for direct feedback. So with that, I'd like to say thank you for your attention. We're just about at an hour, so I'm going to try to answer a few little questions. So I'm looking here to try to see some questions. So the first question that I'll answer, it says, when will this be available? That's, of course, a key question for us. And so we will be announcing and launching this product within the next couple of weeks, where there'll be commercial information available. And so at that point, it would be good to talk to your local sales representative. He can get you some more information, and there'll be full product information at that time. It says here is the software multi-threaded for these speeds? Yes, it is. It is multi-threaded. We take advantage of modern multi-core processors to try to be the most efficient we could get. Another question where it's asking, what is the pattern? How are the patterns saved? The format of pattern saving. And so we save this into an HDF5 file. So the patterns are saved as binary data into this HDF5 file, but those can then be exported as different file formats. If you want just individual patterns, you can export them as TIFFs or bitmaps or JPEGs. You can also export it out to a single, just a stream data file, depending on how you want to read it. I'll read this one because it's there's a question here. It says, when is dictionary indexing available? Dictionary indexing we'll be launching that shortly as well. We call that package OIM Matrix. But it's an add-on that doesn't go into the APEX product. It piggybacks into OIM Analysis, where we'll collect and save the patterns within APEX, but the dictionary indexing is designed to work offline, not as live indexing. And so there's actually a webinar from sometime in the summer by Dr. Stuart Wright, where he went over some of the dictionary indexing functionality. So that will be coming along as well. So with that, just in the interest of time, it's been an hour. If you've submitted other questions I haven't had the chance to answer, we will answer those remotely. I'd like to thank you for your time and attention, and we're excited to present this out to our user base. So with that, thank you very much.